Okay, so since tapos naman na tayo sa determinate torsion, punta naman tayo sa indeterminate torsion. So dito sa indeterminate torsion, gagamit na tayo dito ng approximation saka ng code. Kasi kung ipipilit mo na isolve yung indeterminate gamit ng TOS, kasi bida-bida talaga kunwari, baka pa sana nagsusunod ka pa rin ng design torque. So dito, nag-provide yung NSCP natin ng mga codes para ma-simplify yung solution natin. So dito, ma-apply natin yung mga natutunan natin dun sa one-way slab saka sa two-way slab. Kasi take note na kapag sa slabs, diba, technically, indeterminate system sila. So, ginagamitan natin kunwari dun sa one-way slab ng ACI moment coefficients. And dun naman sa two-way is gumagamit tayo ng coefficients para malaman natin yung partition ng moment na dadalhin ng column strip width and ng middle strip width natin. So, as well as yung beam natin. Okay? So, ngayon, basahin natin muna kung ano yung indeterminate torsion, which is commonly found in the edge beams of floor systems daw. Slabs transfers the negative moments to the edge beam, which in turn transmits it to the supporting columns. Tapos yung columns pinapasa niya sa footing and yung footing pinapasa niya sa lupa. So nabasa ko lang yun sa meme. So ayun, wala lang, share ko lang. The maximum torque occurs in the midspan of the edge beam, where the rotation of the slab is maximum and reduces to zero at the face of the supporting columns. Okay? So, pansinin natin itong floor plan na to. And sabi daw dito, nag-o-occur daw yung indeterminate torsion kadalasan sa edge beams natin. Pero hindi lang yung sa edge beams sa pagkakaalam ko. Nag-o-occur din siya syempre dun sa ating mga middle beams. So ito yun. Kasi, katulad na sinabi ko kanina, kapag naglagay ka ng beam dyan, tapos nag-produce ka ng load dyan, ang tendency is magpo-produce ka ng torsion about dito sa dalawang supporting beams niya. So, ayun lang naman yun. Pero ang kadalasan binibigay dito is yung edge beams talaga. So, ayun, magbasa tayo ngayon ng mga code. So, for the first code natin, factored torsion. So, unless determined by a more detailed analysis, it shall be permitted to take the torsional loading of the slab as uniformly distributed along the beam. So, dito ang gagawin lang natin, hindi na natin bubusisiin kung ano yung mga torque na may experience per length ng beam natin. Kaya, di natin kunin yung torque dito, di natin kunin yung torque dito. Hindi na natin papansinin yung variation ng torque along the beam. I-assume na lang natin siya agad as uniformly distributed. So, ayun nakukuha nyo. So, proceeding sa next sa next code natin, for the factor design torsion, if TU is greater than or equal to the phi TCR and TU is required to maintain equilibrium, the member shall be designed to resist TU. In a statically indeterminate structure where TU is greater than or equal to the phi TCR and a reduction of TU in a member can occur due to the redistribution of internal forces after torsional cracking TU to phi TCR, where the cracking torsion TCR is calculated in accordance with section 422.7.5. If TU is redistributed in accordance with the section, the factor moments and shears used for design of the adjoining members shall be in equilibrium with the reduced torsion. So, di ba, nga pakahaba, dami ko sinabi. I-define muna natin, alamin muna natin kung ano ba yung tinatawag dito ng cracking torsion. So, ito yung cracking torsion natin. So, di ba, natakpan ng beam? So, yung cracking torsion daw natin, ito yung torsion na kailangan ma-experience ng beam natin, such as, magka-crack pa lang talaga yung mga extremes ng beam natin. So, kaya nga siya tinawag na cracking torsion di ba? So, ayun daw yun. So, ang ibig sabihin ng factor design torsion na yung 422.7.3 na provision, ibig sabihin lang niya, kapag daw nag-exceed yung nakukuha na torque ng ating beam sa TCR niya, pwede na natin gamitin yung TCR as the critical torque na lang. Imbes na TU yung gamitin natin, TCR na agad yung lalagay natin kung nag-exceed yung TU natin dun sa TCR. Okay? And in turn, kapag ginamit natin yung TCR, i-redistribute natin ngayon yung uniformly distributed torque na ginamit natin. Okay? So, mamaya, mas maiintindihan sana natin to kapag solve na tayo ng mga problem. So, alamin muna natin yung cracking torsion shall be calculated in accordance with table 422.7.5.1 for solid and hollow cross sections. Pero ang gagamitin lang natin dito is yung solid cross section. And ang gagamitin natin dito is for non-pre-stress member, which is ito. Pero kung binigyan naman kayo ng iba na hindi non-pre-stress member, meron naman sa code. So, tingnan nyo na lang, okay? Pero, as for our case, ang gagamitin natin dito is itong non-pre-stress member lamang. Okay? So, may papansin nyo, meron tayo ditong dalawang unknown Pokemon. Yung ACP natin, saka yung PCP. So, ano ba itong dalawang bullshit na to? So, itong dalawang to is, for your information lamang, yung area na to and yung perimeter na to pertains to the gross section ng beam natin. Okay? So, gross section naman. So, ano ba itong gross section na to? Bago tayo dumako dun, alamin muna natin itong code na to. So, for monolithic or fully composite construction supporting two-way slabs, a beam includes that portion of the slab on each side of the beam extending a distance equal to the projection of the beam above or below the slab, whichever is greater, but not greater than 4 times the slab thickness. So, ang haba na naman, di ba? So, ito lang ibig sabihin yan. For values of ACP and PCP daw, the value of X is the lesser of the value between H minus TS. So, ano ba itong H minus TS na to? Kung babasahin ulit natin yung code, di ba sinabi dito is projection of the beam above or below the slab. So, yan yung HT minus TS na yan. So, dito sa slab na to, di ba ito yung slab natin? Ayan, yung slab natin to, di ba? Sa baba niyan, ito yung projection ng beam natin. Okay? Ito yun. Ito yung hina-highlight ko na section na to. So, ano bang height nito? Diba? Kung ito yung overall height ng beam natin, maminusan lang natin siya ng, diba? Nung thickness ng slab. Therefore, H minus TS siya. And dapat yung value na yun is hindi dapat mag-exceed ng 4 times TS. Pero ang alam ko, yung sinasabi dito na projection ng beam above. Kasi, diba, yung sinabi ko lang na to, diba, below the slab lang siya. Yung above the slab na to, ito yun. Itong portion na to. Okay? Pero, napakadalang kasi na mag-govern yung length na to. Kasi sabi dito sa code natin, pipiliin natin yung greater dito sa above and below. Pero dapat, yung value na makukuha natin sa dalawang yan is dapat hindi siya mag-exceed ng 4TS. Therefore, for simplification purposes, ang ginagawa na lang natin is i-compare natin yung H minus TS and 4 minus TS. Kung sino yung mas maliit na value sa kanila, is sino yung mag-govern. Okay? So, I hope naintindihan nyo. Kung hindi nyo naintindihan, namnamin nyo muna yung slide na to. Okay? And if the maximum torque is reduced to the level of the cracking torque, torque within the beam will be reduced. Okay? So, ito yung sinabi ko kanina, na kapag daw nag-exceed yung TU natin, dun sa TCR natin, gawin na natin critical torque, yung mismo TCR natin. And, in turn, i-redistribute natin yung uniformly distributed torque. Okay? So, note that the phi, or the strength reduction factor, 0.75 for shear and for torsion. All throughout the design process and analysis process, ang gagamitin natin na phi is yung 0.75. Pero, just for your information, kung nung 2001 kasi, ang ginagamit dito is hindi 0.75, 0.85. Well, actually, yun ang talaga yung pinagkaiba nung NSCP 2015 when it comes to torsion and shear kumpara dun sa 2001 and 2010. Kung papansin nyo kasi, dun sa code, kung nagbabasa man kayo ng code, yung mga codes na nilalagay dun sa 2015 is naka-decimal. Samantala, kapag binalikan nyo yung mga dati nating code dun sa 2001, naka-fraction lang sila. So, yun lang naman yung pinagkaiba. And aside from that, ang pinagkaiba nila is yung pagkakagamit nga nung fee natin. Which is dito, sa 2015, 0.75 or 75% na lang nung ating section yung gagamitin natin. Samantalang nung sa 2001, 85% pa yung gagamitin natin. Therefore, sa 2015, mas ginawa nilang mas safe. Kasi 75% na lang yung allowed natin. And may 25% pa tayo na allowance. So, going back, ito yung magiging projected area natin. So, ito yung magiging ACP natin, di ba? And itong X na to, ito yung sinabi ko kanina na H minus TS and 4 times TS. So, ito yung ACP natin, and ito rin makukuha natin dito, yung PCP natin. Therefore, pag kumuha tayo dito ng equation ng ACP and PCP, ang lalabas is ganito. ACP is equals to H times BW plus TS minus times X. Tapos, yung PCP natin is 2 times H plus BW plus X. So, hindi ko naman na kinakabisa yan, kasi more on common sense lang to, and itinyo mo lang talaga yung code. Okay? So, ayun. Ito nga pala yung strength reduction factor na sinasabi ko kanina. So, kung mapapansin nyo, parehas sa strength reduction factor for the shear and for the torsion. 0.75 sila parehas. A one-way slab floor system shown have stringers spaced at 4.2 meters on centers and loaded with a dead load of 5 kilopascals and a live load of 2.4 kilopascals. The factored floor load is W is equals to, ginawa na niya palang W. So, in-evaluate na niya, nakuha niya yung W na 9.84 kilopascals. The slab is monolithically connected with the edge beams that are supported by columns spaced at L is equals to 7.5 meters. The beam width is 270 millimeters and the beam height is 500 millimeters. The columns are 500 by 500 millimeters. Determine the torque at D is equals to 0.43 meters and at 2H is equals to 1 meter. Use FC prime is equals to 28 megapascals and the thickness of the slab is equals to 120 mm. So, ito daw yung magiging floor plan natin and i-design natin yung beam na to. Ito. Ayan. So, kukunin natin yung magiging design torques along that beam tapos ito yung magiging cross-section niya. So, let's solve for the moments na. So, for the moments, ang gagamitin natin is yung ACI moment coefficient. So, kukunin natin yung moment na ma-generate about dito sa point na to. Ayan. So, para makuha to, kung maaalala nyo man sa one-way slab, ginamitan natin siya ng ACI moment coefficient, di ba? Kasi kung titingnan nyo, ito yung cross-section niya, di ba? Di ba kung maaalala nyo, di ba meron siyang ganito? Ayan. Tapos meron siyang mga corresponding coefficients for certain locations nung ating cross-section. Na makukuha natin yung moments. Sa katunayan, na makukuha natin dito is negative moment and equal siya sa 1/24 WU ln squared. So, ayun yung para for discontinuous exterior support. Okay? So, upon solving, makukuha natin yung Mn na equal sa 6.332409 kN per meter. So, ano ibig sabihin nito? So, bale daw, along the length of this beam, magkakaroon ka daw ng moment na equal sa 6.3324. Kaya nga siya kilonewton meter per meter. Kasi uniformly distributed siya sa beam na to. Okay? So, for the critical torque, TU is equals to 6.332409 times 7.5 minus 0.5 over 2 minus 6.33 times 0.43. So, ano ibig sabihin nitong ano na to, equation na to? So, itong itong term na to, kinuha niya lang dito yung torque reaction, di ba? So, para makuha yung torque reaction, ang ginawa lang niya is 6.33 times yung clear span, okay? So, 7.5 minus 0.5 daw. Kasi di ba yung 0.5, yung 7.5 na to, center to center yon. And para mapunta ka sa clear span natin, babawasan mo siya ng isang column dimension, which is yung 500 millimeters. Tapos, i-divide mo siya ng 2 para makuha mo yung torque reaction. Kasi, since uniformly distributed naman siya, di ba? And then, maminusan mo siya ng uniformly distributed the torque multiplied by the value of D, which is yung 0.43 meters. So, makukuha natin yung critical torque doon at a distance D. For the critical torque, makukuha daw natin siya as 19.44 kilonewton meter. So, gagamitin na ba natin to? Hindi pa, kukunin muna natin yung ating cracking torsion. Okay? So, tapos, i-check natin kung nag-exceed ba itong TU na to dun sa cracking torsion natin. Okay? So, solving for the value of X, kasi isa-solve natin yung value ng X, since sinabi doon, monolithically connected daw yung slab and yung beam natin. Therefore, itong beam section na to, which is yung dulo natin, is mag-extend pa about an X distance, which is ito. Therefore, ito yung magiging total na gross section ng beam natin. Okay? So, sana naiintindihan nyo. And, solving for the value of X, makakuha tayo ng 500 minus 120, 380, and for the 4 times the thickness of the slab, which is 120, 4 times 120 is equals to 480. Therefore, kukunin natin dito yung mas maliit na value, which is yung 380 natin. Okay, so ma-solve na natin ngayon yung value ng TCR natin. Since makukuha na natin mula dun dito sa value ng X na yan, yung value ng ACP natin and yung PCP natin. And therefore, pag isunod natin yan, 0.75 times 0.33 square root of 28, which is yung FC prime natin, times yung ACP, so 270 times 500, ito yun, yung beam width daw natin na 270, multiply lang natin sa beam height natin, tapos yung X daw natin, i-multiply natin dun sa thickness ng slab natin. Therefore, makakuha natin yung ACP. And yung para sa perimeter naman, alam nyo na yan, okay? So, times 10 raised to negative 6 para maging kilonewton meter. So, ang magiging sagot daw natin is 18.57 kilonewton meter. Ngayon, since 19.44 is greater than 18.572, which is yung cracking torque natin, torque can be reduced to the cracking torque itself. And ngayon, i-redistribute natin yung torque since nag-adjust ngayon yung TU natin, di ba? So, magbabago ngayon yung uniformly distributed torque na ipapatong natin dun sa ating beam. So, makakuha natin yun by this equation. T is equals to PTCR over ln over 2 minus D. So, ano ba to? So, yung equation na to is nakuha lang to dito. Okay? So, the same way kung paano natin kinuha yung critical torque. So, bale, ang ginawa niya lang dito is in-rearrange niya itong equation na to in such a way na yung TU daw natin is magiging 18.572 na and ang magiging ano natin or yung naka-isolate sa isang side is itong 6.332409. Pero this time, unknown na yung value na to. Kaya ginawa natin T. Okay? So, ayun, upon solving, makakuha natin yung bagong value ng uniformly distributed torque which is equals to 6.04956 kilonewton meter per meter. So, in-adjust natin. Okay? Therefore, makakuha tayo ngayon bagong value for the design torque at D, which is equals to 18.572 and design torque at 2H, which is equals to 15.124 kilonewton meter. Okay? Therefore, ito na yung magiging design torques na gagamitin natin for the design and analysis process. Okay? Punta tayo ngayon sa threshold torsion. So, dito, as the name says, ito yung torsion na kayang dalhin ng ating beam naturally. Yung wala pang design. Kumbaga, by nature, ito yung kayang dalhin na torsion nung mismong section natin or nung mismong beam natin. Kumbaga, kung iisipin natin, kapag yung na-develop natin na torque dun sa beam, is hindi naman lumagpas to sa threshold torsion. Kapag wag ka na mag-design talaga for torsion kasi di mo naman talaga kailangan. Kayang-kaya na pala ng beam na i-resist yung torsion na may experience niya. Kasi hindi naman siya lumagpas sa threshold torsion natin. So, the limit torsional force that can be absorbed by the beam without any detrimental effect such that the torsion can be neglected. Ayun, katulad nga ng sinabi ko, ayun yung meaning ng threshold torsion. So, ito yung magiging code na mag-govern for D para sa threshold torsion. So, masasolve natin siya. Ang papansinin natin dito is yung for solid cross sections and yung for non-pre-stress member. Which is ito. Ito yung magiging equation natin. Okay, so ngayon, pumunta tayo sa problem solving. Determine the threshold torsion for the edge beam section in example 2 or yung previous example natin and compare it with the design torque at distance D from the support. Okay? So, kukunin natin to, formula na to, i-apply natin, kukunin natin yung threshold torsion, and i-compare natin siya doon sa na-compute natin na design torque kanina para malaman natin kung dapat ba talagang i-design natin to for torsion or hindi naman na kailangan. Okay? So, For the threshold torsion, upon solving, kapag in-apply lang natin itong formula na to, meron naman tayong value ng ACP and yung PCP as well as yung FC prime. Therefore, makukompute natin yung threshold torsion, which is equals to 4.671 kN. And ayun, kung nagtataka kayo kung saan ba na-derive itong mga formula na ito ng threshold torsion, pati yung cracking torsion, kasi kung mapapansin nyo, di ba magkapares na sila? Well, it came from the concept of shear flow talaga. Shear flow. So, kung gusto yung alamin, okay lang din naman. Pero, hindi ko na siya pero hindi ko na siya sisinin dito kasi medyo out of scope na yun. Medyo mahabang usapin kung i-discuss ko pa kung ano yung shear flow. So, yung shear flow is matatakan nyo sana from the strength of material subject. Okay? So, ayun, dun lang naman ang galing ng threshold torsion na to. And since mas malaki siya dun sa ating threshold torsion, ang mangyayari is i-consider na talaga natin or i-design natin yung torsion natin. Kasi hindi natin siya pwede i-neglect. Okay? Therefore, the torque has to be considered when designing. Take note that the TCR is always greater than the threshold torsion. Therefore, di ba dun sa TCR pa lang, nag-check na tayo kung lumagpas ba yung design torque natin dun. Therefore, kung lumagpas na yung design torque natin or yung pinakauna nating design torque sa TCR, hindi na natin kailangan i-check kung naglumagpas pa siya sa threshold torsion. Kasi by nature, mas mataas ang cracking torsion kaysa sa threshold torsion natin. Therefore, matik na kailangan mo i-design talaga for torsion yung ating section or yung ating beam. Okay? Okay, so hindi lang threshold ang kailangan natin i-check. Need din natin tingnan kung adequate ba yung beam section natin para ma-design sa torsion. Okay, sabi mo, yes, kailangan na i-design natin yung beam for torsion. Pero you need to consider if kaya ba talaga ng beam section mo yung mako-compute mong design. Di ka ba na trying to say? Diba? Parang ganun yung concept nito. Therefore, i-check natin yung cross-sectional limits ng ating beam section. Okay, so for the cross-sectional limits, meron tayong susundan na code. Cross-sectional dimension shall be selected such that A or B is satisfied. Okay? For solid sections, ito yung magiging formula. And for the hollow sections, ganito yung magiging formula natin. Ito lang yung gagamitin natin. Okay, so for solid sections lang, which is ito. Kung papansin nyo, meron naman tayong dalawang bagong variables, which is yung pH and yung AOH. So, ano yung pinagkaiba nila? So, the AOH kasi is the area enclosed by the center line of the outermost closed transverse torsional reinforcement, and pH is the perimeter of the center line of the outermost closed transverse torsional reinforcement. So, ano ibig sabihin yan? So, ito yun, given siya by this figure. Okay? So, yung AOH natin is yung mismong core na ine-enclose nung ating transverse torsional reinforcement. Kasi di ba stirrups to? And mag-form yung stirrups natin na parang hoops, di ba? So, ito yun, yung na-enclose na itong stirrup na to, ay yung AOH natin. And yung pH natin is yung perimeter nung mismong nung mismong core na to. In which yung dimensions niya is yung center line nung opposite na stirrup bars, which is yung XO natin and yung YO. Kasi measured sila mula doon sa center line. Kung mapapansin nyo, di ba? Okay, so balik tayo dito ngayon sa formula natin. So, pansinin natin itong second term na to, where the value of VC for simplified computations, di ba kasi may VC tayo dito? And kung maaalala nyo sa shear, for simplified na VC, ito daw yung formula niya. 0.7 lambda square root of FC prime BW times D. Where yung lambda natin is pwede na natin iset as 1. Kasi kung for normal weight of concrete, which is kadalasan yun naman yung ginagamit natin, magiging 1 lang yung lambda natin. And yung 0.17 natin is ganito, magkakaroon niya ng magic mamaya. So, pwede natin ipalit to, isubstitute natin yan dito, and ito yung magiging result ng equation. Tapos, makakancel natin dito yung BW and yung D. Okay? BW and D is cancelled. Okay? So, matitira na lang dito, technically, is 0.17 square root of FC prime plus 0.66 square root of FC prime. Ngayon, pwede natin ipag-add yung dalawang yan. Okay? Na decimal lang. For more accurate solutions, ang gagawin natin is gagawin natin silang fractions. Kasi, katulad nga sinabi ko sa inyo kanina, yung codes na ginagamit for 2015 NSCP is same lang naman halos sa 2001. Ang pinaka-difference talaga nila is ginawa lang nila tong decimal. Compared sa dati na naka-fraction form. So, yung 0.17, di ba pwede natin yung iset as 1/6 and yung 0.66 galing lang sa 2/3, di ba? Therefore, kapag pinag-add natin yung dalawang yan, ang magiging resulting equation natin is P 5/6 square root of FC prime. So, mas madali itong tandaan kesa dito, di ba? So, ngayon, himayin pa natin lalo itong equation na to or itong sinasabi ng code natin ng NSCP. So, ganito kasi yan. Itong section na to or itong terms na to, ito yung tinatawag natin na developed stresses. Okay? Ito yung stress na dadalhin ng ating section. Tapos, pwede natin siya hatiin sa dalawa. Yung unang term natin, which is VU over BW times D, is yung para sa shear, di ba? Kasi kung mapapansin nyo, VU nga eh. So, therefore, shear yung kino-consider natin dito. Tapos, itong equation na to, na-derive lang naman to sa force over area, di ba? Itong VU na to, ito yung shear force at that section, at that specific section. And yung BW times D, ito yung area, di ba? Ano may formula ng stress? Yung force over area, ganun lang din yun. Tapos, yung sunod na term naman, which is yung TU of PH over blah 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 blah. So, itong torsion na to, kung papansin nyo, nagkakahawig sila nung formula nung cracking torsion saka ng threshold torsion, di ba? So, kung matatandaan nyo, yung threshold torsion, ganito yung itsura, di ba? So, kung i-rearrange natin tong threshold torsion na to, di ba yung threshold torsion natin, T, set natin siya as T, okay? Tapos, itong PCP, iangat natin dito, di T times PCP na. Same analogy as TU times PH. And yung ACP squared, binaba. Okay. Ang matitira dito is yung stress term. Ito na lang. Ito yung matitira dyan. Kasi aangat ng PCP and bababa tong ACP squared. So, same way dito sa torsion na to. So, kung mapapansin nyo, halos same lang talaga sila ng concept. Ang pinagkaiba lang, dun sa threshold torsion saka sa cracking torsion, ang kino-consider natin is yung gross section ng beam natin. Samantalang dito sa developed stresses, ang kino-consider natin dito is yung core na nung ating beam mismo, which is yung ito. Which is ito, yung na-enclose nung stirrups natin. Okay? So, yun lang ang pinagkaiba nila, pero magkakahawig lang talaga sila. Diba? So, kung ang tawag dito sa dalawang to is the developed stresses, ano tawag dito? Tawag mo dyan is the resistance of concrete. Okay? Where the shear is VC over BW times D. Kasi tandaan nyo, yung VC, diba ito yung yung shear na dadalhin ng concrete natin. Diba? Tapos yung torsion is 0.66 square root of FC prime. So, ang dadalhin lang daw na torsion ng ating concrete is 2/3 lang ng FC prime natin dapat. Okay? So, paano natin magagamit to? So, dapat daw, yung developed stresses daw natin is less than or equal to dun sa resistance ng concrete natin. Bakit? Kasi ganito, kapag nag-exceed yung developed stresses natin dun sa resistance ng concrete, mawawasak yung mismong concrete ng beam natin. Diba? Therefore, kailangan mo i-adjust yung beam sizes natin bago natin siya i-design for torsion muna. Okay? So, kailangan kasi maging adequate yung section na yun to resist torsion. Okay, so punta tayo sa problem solving. So, itutuloy natin yung problem natin kanina. Check the audacity. Ha? Bobong putik. Mali yan. Adequacy to. Ano to, lutang na ba ako? Check the adequacy of the beam section against the maximum shear and torque. Apply a wall load of 9 kN per meter on top and centered on the edge beam. Use a concrete cover of 50 mm, main bars of 20 mm P, and two-legged 10 mm diameter stirrups. So, ito yung mga nakuha natin kanina mga data na magagamit natin ngayon. So, ngayon, punta na tayo sa solving. So, ang una natin kukumpitin dito is yung shear force at a distance D. Okay? So, para makuha yun, ang gagawin natin is ganito. Floor load is equals to W times L over 2. In which yung W natin is 9.84 over 2 times yung 4.2 minus 0.27. Take note na kung hindi na naalala yung figure, ganito yung tsura nun. Diba ito yung edge beam natin, meron tayong supporting column dito, and ito yung S natin, diba? Ito yung S, okay? Tapos, kaya natin dinidivide ng 2, kasi kalahati lang naman yung dadalhin ng edge beam na to na tributary area, okay? Divided by 2. And kaya natin minus yung 0.27 na beam width, is kasi kailangan lang naman natin yung clear span ng ating beam, okay? So now for the beam weight, since floor load lang to at hindi pa kasama dito yung beam weight, kukunin natin yung beam weight. Beam weight is equal to 0.27 times 0.5 times 24. 3.24 yung magiging beam weight natin. And for the total beam load, idadagdag na natin siya ngayon. So, 19.336 plus 1.2 times 3.24 plus 9. So, take note na 1.2 kasi pares naman silang dead load ng beam weight natin. Okay? So, yung floor load natin is nakumpita natin ito 9.84 kanina dun sa previous problem. Tapos, ayun, for the total beam load, makukuha natin siya as 34.024 kN. Ngayon, for the shear force at a distance D from the support, masolve natin siya by this one. W times L over 2, ito yung magiging reaction at the support, diba? Minus W times D. Okay, so mapupunta ngayon dun sa shear force at a distance D. So, I hope natatandaan niyo pa or na-visualize yung shear diagram. Is equals to 104.45 kilonewtons. And take note, yung B natin is equals to 270 and yung D natin is ganito. 500 minus 50, which is yung concrete cover, plus 10 na stirrups, plus yung kalahati ng bar diameter natin. So, mapupunta ka na nun dun sa centroid ng reinforcing bar natin. So, 430 millimeters. Okay? So, kung mapakita natin ngayon yung figure, ito yung magiging itsura niya. So, ito ngayon yung B, and ito ngayon yung magiging H natin. And ito yung magiging D natin. Mula dito hanggang dito. Okay? Somewhere dyan. So, nasan man yung reinforcing bar natin. So, ngayon, kukunin natin yung XO, pati yung WO. So, yung XO natin, makukuha natin is ganito. 270 minus 2 plus 50 plus 10 over 2. So, paano nangyari to? So, 50, ano ba yung concrete cover? Di ba mula dito hanggang dito is 50. plus ng kalahati ng stirrups natin, which is 10/2. So, pupunta ka na dito sa centroid ng ating beam. So, since yung BW natin is itong isang buo, minusan mo ng distance sa to at distance sa to, ang matitira is yung XO, di ba? The same logic na gagawin natin para doon sa YO. Pero this time, 500 yung gagamitin natin na value, na overall value. Minus 2 times 50 plus 10/2, makukuha natin na value for XO is 160 and for YO, which is 390 millimeters. So, makukuha na natin yung value ngayon ng AOH and PH na by common sense na lang yan. So, AOH is equals to 62,400 millimeters squared and PH is equals to 1,100 millimeters. So, ngayon, makukuha na natin yung value ng developed stresses natin. So, paano yun? So, for the developed stresses, unahin natin for shear, VU over BW times T. Yung VU is na-compute natin kanina, 104.45 times 1,000 para maging Newton and over 270 times 430. Makukuha natin itong value na to, which is 0.9 megapascals. And for the torsion, TUPH over 1.7 A squared OH. So, meron tayong TU, meron tayong PH, times natin ng times 10 raised to 6 to, para maging Newton millimeter. Okay? So, ang magiging sagot is 3.08 megapascals. So, yun yung developed stresses natin. And para makuha natin yung overall stresses or yung combined stress na mararanasan ng beam section natin, ito yun. Gagamitan natin sa Pythagorean theorem and makakuha natin yung value na 3.2147 megapascals. Okay? Ngayon, kukunin natin yung resistance ng concrete which is given by this formula. Yung na-derive natin kanina na phi quantity 5/6 square root of 28. So, equal siya sa 3.307 megapascals. Since yung resisting stresses natin is greater than dun sa developed stresses natin, therefore, yung section daw natin is adequate to be designed for torsion. Therefore, wala tayong gagawing revision in terms ng dimensions ng beam natin. And okay lang siya i-design for torsion. Note if developed stresses is greater than the concrete resisting stresses, redesign the beam dimensions. So, yun yung sinasabi ko kanina, na kapag lumaki yung developed stresses kumpara dun sa resisting stresses ng concrete natin, kailangan na natin i-redesign yung beam section natin. Kasi hindi niya talaga kakayanin kahit i-design mo pa siya ng torsion.